Hi, it's Bruce, and welcome once again to my Rocky Mountain Lab. And what I'm looking at today is primarily to demonstrate this 3320B frequency synthesizer. This was made by Hewlett-Packard back in the 70s, somewhere between 71 and probably 78. I'm not exactly sure on this particular unit, but it was a breakthrough. Uh, Gives you a dialed in frequency from a few millihertz all the way up to about 13 megahertz. And on top of that, it gives you a remarkable control over the amplitude into 50 ohms. Yeah, I'm calibrated here, so for instance, right now we have 0 dB selected, 0 dBm selected into this 50 ohm 50 ohm DC input on the Tektronix 2465. I've moved my my cursors for voltage measurement to the tips of the waveform, and I'm showing 632 millivolts of output, which if you look it up, that's into 50 ohms. That would be 0 dB. And as I dial these things, I've tried several combinations, and we'll demonstrate that in a bit. But it's always been right there, and any error that I see pretty much can be me moving the cursors. And when we're talking something on the order of a 0 to 2 or 3 millivolts difference. So it's remarkable. I am impressed with that. Frequency response is right on the nose as well. You give this unit a chance to warm up for about an hour. Alright, so you can see I've added in a frequency counter here. And right at the moment, that counter is telling me that this 100 kilohertz signal from the 3320 is coming in at 99.99989. So rounding a little bit there, we'll just call it 49. So we're 99.9999. So that's a tenth of a kilohertz off of a perfect 100 kilohertz. Let's go ahead and take her up in frequency. All right, here's 1 megahertz, and we are reading 999.999. So we are now 1,000th of a kilohertz off. So we're 1 hertz off of a perfect 1 megahertz coming out of the unit. And that's using the internal counter that is in this frequency counter too. So could be an error off of that frequency counter, accounting for part of that 1 hertz. And as you notice, we're still within the boundaries of that 632 millivolts, the 0 dB output. And as I change the frequency, there's 2 megahertz, 3 megahertz. Notice the counter, and notice the waveform within the boundaries of that 0 dB mark. We're maintaining our output and we're maintaining our frequency very tightly. It's 5. Let's go up. There's 10. So 9,999.99 kilohertz out of that unit. And that would be, right now we're 0.989, we'll say. So that would be 0.011 kilohertz off of perfect 10 meg, which would be what, about 10 hertz out of 10 meg, something like that, 11 hertz out of 10 meg. It's an impressive unit. We're going to play around with the amplitude a little bit just to prove that it's working good, so bear with me. Okay, well, we proved that the frequency is pretty much right on, and we are now going to take a look at the power output, the attenuation on the output in dBm, and check a few points. So right now we're back at 0. We mentioned this earlier. This is 0 dBm, and we are getting 0.632 or 632 millivolts, which is right on the nose for 0. Well, let's say we had a 1, and let's decrease that so we can get it on the screen there. Then we'll go ahead and we'll try and measure it using these cursors. Okay, and I'm getting about 0.715 on the screen, and at 1 dBm, positive 1 dBm, it'd be 0.7096 or 0.71, so within 5 millivolts of being perfect, and that's probably me. If I just make a slight correction here, there's 0.71, and you can't see that that's not correct. I can't see it. So anyway, let's move on. We'll try 2. Let's go positive 2. Okay, and we'll try and get that on the cursor on the tip of the sine wave, and then the opposite, and we're getting whoops. All right, I'm getting 0.8, and 2 is 0.796. So again, just a slight correction, and we would be there. So yeah, again, 0.795, 0.796. Within 1, and you can't see the error on the screen. It's there. So let's go ahead and check -1. We'll make this negative. Make that a 1. Okay. And let's go ahead and turn ourselves back up again. And then we'll go ahead and take a look at the voltage again using the cursors. Alright, okay, I'm getting 0.566, and for a -1 it's 0.564. So it's right on the money there. Let's go ahead and do -2. Okay, and let's get those adjusted again. Okay. Alright, I'm getting 504, and the -2 is 502, so within 2 millivolts, and again, probably me. -4.36. We're getting a little more complicated. Okay. Put her on the... All right, I'm getting 386 on the screen, 386 millivolts, and a -4.36 is 383. So we're within 3 millivolts, and again, that's probably me just setting those endpoints and reading it off the screen. Let's get more complicated a little bit. 9.5. All right, and let's go ahead and give ourselves a little bit more amplitude here. 9.5. And I'm getting 214. 9.5 is 212. So within 2 millivolts. So tracking beautifully. I think you can assume this thing is accurate. It's just me adjusting the lines to the curves that's causing the minimal error that we have there, but it's right there. Okay, so I've connected up my Keithley 2015 total harmonic distortion meter, and we are feeding it from the generator, and we are also feeding it into the oscilloscope, which has a 50 ohm load. So we're loading at 50 ohms, and the meter is able to read the voltage properly, and we're getting our harmonic distortion relative to 50. So let's turn it up a little bit. Okay, so right now I am at 20 kilohertz, and which is of course the upper end of my distortion meter, and I'm getting about 0.019%. So let's make it 0.02% at 20 kilohertz. And as I dial down at 2 kilohertz, about 0.02 still. Okay, at 200 hertz, I'm rising. I'm running about 27, almost 0.03%. And then at 20 hertz, I'm up to about 0.05. So 0.05 at 20 hertz, and then goes up to about 0.02 or down to 0.02 at 20 kilohertz. The spec on the generator says less than 0.1% at full output on any range. I can't test anything outside of the audio ranges, so I'm going to assume that that's pertinent to the higher frequencies more than it is to this audio frequency, just because what I'm measuring. But it is a low distortion device, which is how they build it. Okay. I have this old Hewlett-Packard 332A distortion analyzer, and I wanted to give it a try and see how it did. And this analyzer takes a little bit more work. Basically what it is a notch filter placed between a preamplifier and an output amplifier. And with a notch filter, you pass all of the frequencies coming into the unit except for a very specific frequency that you select. And that's the fundamental frequency of the generator that you're wanting to analyze. By knocking out the fundamental frequency and making it zero, the output zero, or essentially, and then measuring what's left over, amplifying and measuring what's left over, I'll put it that way, you are looking at the harmonics that were generated within the unit during the amplification process, and The unit then will be able to calculate by the output voltage and comparing it to the input voltage what the harmonic distortion is. That's the thumbnail of how this whole thing works. You can read about it more by looking up the 332 and studying notch filters a little bit. It's a bit more work, and it's very sensitive. But let's go ahead and demonstrate it. Let me see. I will. First of all, I want to take the sensitivity down, and then I want to deliberately guarantee that my frequency of my notch filter has not been set. And we'll also play around with the balance control here. Okay, this is all part of the... We can even change the frequency range. So right now what I'm putting in out of this 3320 is 6 kilohertz at 0 dBm into 50 ohms. And I can take a look at the set level, and what that's telling me right now is I've got just about, there we go, it's registering 0 dBm on the meter right now, which is good for what I'm doing. Then if I put myself into distortion mode, okay, and I say, okay, well, I know right now 600 is 10 times less. It's 1/10 of 6,000. So I know I'm not close there. So let's go to thousands, and I see that my needle just dropped a little bit. And then we're going to try and tune this oscillator, actually notch filter. It's not an oscillator, excuse me. I'm going to tune this notch filter. Now you notice that the needle is starting to fall as I get closer to 6,000. And that's exactly what I want. I'm approaching the notch. At some point I should hit a minimum and I should start coming back up. Now you see it coming up? I'm going to go back down to that minimum. See if I can figure out where it is. It's right about there. Yep. Okay, now I'm going to change my sensitivity. All right. And adjust myself again till I'm at minimum. Okay. Now I'm going to play around with my balance level here. And, oh man, that made a heck of a difference. Look at that. This is my coarse balance. Now I can turn my sensitivity up more. It's a sensitive knob a little bit. Could use some pot spray. Okay, and now that was the red coarse button. Now if I turn the black fine control, I should be able to finally maximize. Okay, now we're going to turn our sensitivity up again. I think I can even do it again. And then let's check our notch frequency here, because every time I make an adjustment to a switch level and everything, changes all of the adjustments just slightly. This is what I meant by being a much more difficult measurement. Alright, well, it looks to me like what it's telling me here is that if I'm on this 0.003 setting, then I go out here and I'm reading on the 0 to 1 scale, and 1 is 0.1. So I divide everything by 10. So I'm getting 0.64 divided by 10 would be 0.064% of harmonic distortion, which is, you know, it's in the same realm as what I got with the Keithley. It's not exactly the same value. Certainly within the same decade. Less than 0.1% for sure, where I was able to get, boy, that's sensitive. We'll get you. All right, about there. So that's a demonstration of how that works. Now, I was getting 0.04% at 20 hertz, 0.05%, excuse me. At 10 kilohertz, I was getting 0.02 on the Keithley. Well, it looks like I got a reading of 0.01% on the Keithley at 6 kilohertz versus 0.064% on the 332A. So I'm not sure which one is accurate in these readings. I've not had a calibration on either one of these devices, so they're both susceptible to have some error. In terms of the technology, I would tend to think that the Keithley up there at the top on the right is accurate. However, I find it extremely odd that HP would have rated the 3320B generator at less than 0.1%, unless it was, you know, somewhere relatively, you know, in deep into the realm of 0.1%. In other words, 0.05 would be a likely percentage of distortion. And the 332A gave me 0.064, which is pretty close to the 0.05. So for that reason, I tend to want to believe that the 332A is the accurate device here. Be interesting to know. All right, but I don't feel like, you know, I did badly with either one of them. They're both at least in the same realm, 0.01 or 2% to 0.06%. Not bad. Oh, by the way, I always try to include a manual on CD containing maintenance and user information as well. So that'll be included in all of my sales. And outside of that, happy bidding, huh? Bye. Thanks for listening.